What if the night sky you see is lying to you? Those few thousand stars you can count, they aren't the universe. They are barely the surface. Beyond them exist 200 billion trillion suns. And tonight, we're going to understand why that number changes how you see everything. Tonight, we begin a journey that starts with a question so simple it almost feels childish, yet so deep it stretches the limits of human understanding. How many stars exist in the universe? At first glance, it sounds like the kind of question that should have a neat answer, a number you can write down, memorize, and move on from. But the moment you seriously try to answer it, you realize something unsettling. This is not just a question about astronomy. It's a question about scale, about perception, about the limits of the human mind itself. By the end of this journey, you will not only have a number, you will understand why that number feels impossible to truly grasp, and why that feeling itself tells us something profound about our place in reality. Before we talk about stars, we need to talk about how the human brain handles numbers, because this is where everything begins to break down. Every day, without thinking about it, your brain estimates quantities. You walk into a room and instantly know if there are 3 people or 10. You glance at a table and know if there are 5 objects or 12. This ability feels effortless, almost automatic, but there is a limit. For most humans, that limit sits somewhere around 15 to 20. Beyond that, precision collapses. Is that group 40 people or 60? Is that crowd 200 or 300? Without counting, most of us simply cannot tell. This isn't a flaw in intelligence. It's a feature of evolution. Our ancestors needed to make quick decisions about small numbers. How many predators? How many allies? How many animals in the herd? These were survival questions, and they rarely involved large quantities. Because of this, our intuition was never designed to handle big numbers. When someone tells you that a stadium holds 70,000 people, you accept it intellectually, but you don't feel what 70,000 means. You can't picture it the way you can picture 5 people standing in front of you. The number becomes abstract. It becomes a symbol, not a lived experience. And this becomes a serious problem when we talk about stars, because the numbers involved are not just large. They are far beyond anything human intuition can naturally process. So, before we look up at the universe, we need to build a ladder for the mind. We need to slowly climb through scales of numbers until we reach the edge of what feels meaningful. Let's start small. 1,000 seconds is about 16 minutes. You can wait that long without effort. You could count to 1,000,000 if you wanted to. It would be exhausting, but it's conceivable. 1,000,000,000 seconds is 32 years. If you started counting the moment you were born and never stopped, you would reach 1 billion sometime in your early 30s. To count that high, you would have needed to start before the invention of agriculture, before cities, before written language. Every empire in human history would rise and fall while you were still counting. Notice something important here. The difference between 1,000,000 and 1,000,000,000 is not just a bigger number. It's 1,000 times bigger. The difference between 1,000,000,000 and 1,000,000,000,000 is another 1,000 times. These are not steps, they are cliffs. But we're not there yet. First, we need to look at what we can actually see. On a perfectly dark night, far away from city lights, with clear skies and good eyesight, you can see somewhere between 2,000 and 5,000 stars with the naked eye. The exact number depends on where you are and how long you let your eyes adjust to the darkness. Let's be generous and say 4,000 stars. That is the entire visible universe for the human eye without instruments. And here's the first revelation. Every single one of those stars is inside our own galaxy, not scattered across the universe, not distant cosmic beacons from the edge of time. They are all neighbors, astronomically speaking. When you look up at the night sky, you are not seeing the universe. You are seeing your immediate neighborhood. The Milky Way is a vast, barred, spiral galaxy, about 100,000 light-years across. Our Sun sits roughly 26,000 light-years from the center, embedded in one of the spiral arms. That faint, milky band stretching across the sky on dark nights isn't a cloud. It's the combined light of millions of distant stars, too faint to resolve individually, blending together into a soft glow. Ancient humans saw it and wondered. It took telescopes to reveal the truth. When Galileo first pointed a telescope at the sky in the early 17th century, he made a discovery that shattered the old worldview. That glowing band was not mist. It was stars, countless stars, extending far beyond what the naked eye could see. And every improvement in telescope technology revealed more. Bigger lenses gathered more light. Clearer optics resolved fainter points. The number of visible stars exploded. Thousands became tens of thousands. Tens of thousands became millions. And still, this was only our galaxy. This raises the next question. How many stars are actually in the Milky Way? The honest answer is that we don't know exactly, and that uncertainty is important. We can't simply count them one by one. Dust clouds block our view of large portions of the galaxy, especially toward the center. Most stars are incredibly dim. Red dwarf stars, which make up about 70 to 75% of all stars, are so faint that not a single one is visible to the naked eye, even though they dominate the stellar population. And we are inside the galaxy. We are trying to measure, like trying to count every tree in a forest while standing in the middle of it. Astronomers work around this using clever methods. They count stars in small regions where visibility is good and extrapolate. They measure the total mass of the galaxy through gravitational effects and estimate how much of that mass belongs to stars. They compare the Milky Way to similar spiral galaxies and use them as templates. None of these methods is perfect, but when independent approaches converge on similar results, confidence grows. Today, the best estimates suggest that the Milky Way contains between 150 billion and 250 billion stars, with most estimates clustering around 200 billion stars in our galaxy alone. If you counted them one per second, it would take over 6,000 years. You would need to have started counting before the pyramids were built. And remember, you can only see about 4,000 of them with your eyes. For every star you can see, there are roughly 50 million you cannot. 200 billion already feels enormous. But here is where the universe pulls the rug out from under our intuition. For most of human history, people believed the Milky Way was the entire universe. Those faint, fuzzy patches in the sky were thought to be gas clouds within our galaxy. Some of them were. Others were not. In the early 20th century, astronomers finally settled a debate that had lasted for centuries. Using powerful telescopes, they discovered that some of those fuzzy patches contained individual stars, and not just any stars. They contained variable stars whose brightness could be used to measure distance. If you want to understand how many stars there are, you first have to accept something uncomfortable. Your brain was never built to understand numbers this large. It's not because you're unintelligent, but because evolution had no reason to prepare you for cosmic scale. For almost all of human history, survival depended on small quantities. How many people are nearby? How many animals are in the herd? These numbers rarely went past a few dozen. Even now, you can glance at a room and instantly know if there are 5 people or 10. You can feel the difference between 1 and 3. But once numbers get too big, your intuition collapses. Try to instantly feel the difference between 40 and 60 people without counting. Most of us can't. We know the difference intellectually, but not emotionally. This limitation becomes a huge problem when we try to understand the universe, because the universe doesn't operate on human scales. It operates on numbers so large they overwhelm the very idea of quantity. So before we talk about stars, we need to rebuild your sense of scale from the ground up, slowly and calmly. Let's start with time, because you experience it every moment. 1,000,000 seconds sounds abstract, but it's only about 11.5 days. You could count to 1,000,000 in less than 2 weeks if you never slept. Exhausting, but you can picture it. You've lived through longer stretches of boredom. Now, 1,000,000,000 seconds changes everything. 1,000,000,000 seconds is about 32 years. If you started counting at birth and never stopped, you'd hit 1 billion sometime in your early 30s. Your entire childhood, your education, your first job, all of it would vanish into that single act of counting. 1,000,000,000,000 seconds breaks our intuition completely. 1,000,000,000,000 seconds is roughly 31,700 years. To count that high, you would have to start before agriculture, before cities, before writing itself. You'd have been counting while humans hunted with stone tools during the last ice age. Every empire in history would rise and fall, and you still wouldn't be finished. This isn't just bigger. It's a different category of magnitude. Hold that feeling, because when we talk about stars, we don't stop at trillions. We go far beyond them. But before we leave Earth, let's ground ourselves in what you can actually see. On a truly dark night, far from city lights, the human eye can see between 2,000 and 5,000 stars. Let's call it 4,000. This is what ancient humans saw. This is what shaped their myths, constellations, and calendars. Every single one of those visible stars belongs to our Milky Way galaxy. Not one lies beyond it. Even more surprising, they're all in our local neighborhood, just a few hundred light years away. When you look up at the night sky, you are not seeing the universe. You are seeing your local street. The Milky Way itself is enormous, a spiral galaxy about 100,000 light-years across. Our Sun is about 26,000 light-years from the center, quietly orbiting in a spiral arm. When you see that pale, milky band stretching across the sky, you're looking through the galaxy's disk edge on. That glow, Iason T Gasset, the combined light of millions of distant stars, too faint to see individually. The farthest star visible to the naked eye is about 16,000 light-years away. That means your unaided vision captures less than 1% of the galaxy's diameter. 99% of the Milky Way is completely invisible, without instruments. Telescopes shattered this illusion of scarcity. When early astronomers first pointed lenses at the sky, they discovered that darkness was just an illusion. Every improvement in optics revealed more stars. Where the eye saw emptiness, telescopes found structure. Thousands became millions. Millions became hundreds of millions. The problem then became how to count them. You can't exactly count something you can't fully see while you're standing inside it. So, astronomers got clever. They counted stars in small, clear regions and extrapolated outwards. They measured how fast stars orbit the galaxy to estimate its total mass, then calculated how much of that mass must be stars versus gas or dark matter. They compared the Milky Way to other similar galaxies, and amazingly, all these different methods led to the same range. Our Milky Way contains somewhere between 150 billion and 250 billion stars. Let's use 200 billion as a good estimate. That means for every single star you can see with your eyes, there are roughly 50 million you cannot. This fact alone would have stunned humanity for most of history. But it was only the beginning. For centuries, astronomers believed the Milky Way was the entire universe. Those faint, fuzzy patches in the sky were called nebulae and thought to be gas clouds inside our own galaxy. One of these patches was Andromeda. Everything changed in the early 1920s, when new measurements revealed that Andromeda was far outside the Milky Way. It was another galaxy, containing its own hundreds of billions of stars. In an instant, the universe expanded from one galaxy to many. Once astronomers knew what to look for, they started seeing galaxies everywhere. Deep telescope images showed that what looked like empty space was actually packed with them. In the 1990s, the Hubble Space Telescope stared at a tiny patch of sky larger than a grain of sand held at arm's length for days. That tiny patch contained thousands of galaxies, thousands, each one a massive system of stars. Multiply that across the entire sky, and the numbers just explode. Modern surveys now suggest the observable universe contains around 2 trillion galaxies, not millions, not billions, trillions. Some are small, with just a few billion stars. Others are giants, with trillions of their own. On average, a typical galaxy probably contains around 70 to 100 billion stars. So, let's do the math. Multiply that by 2 trillion galaxies, and the result is almost absurd. 200 billion trillion stars. That's a 2, followed by 23 zeros. A number so large it barely fits inside language. To give this some meaning, let's use a comparison. There are roughly 7 to 12 quintillion grains of sand on all of Earth's beaches combined. That means for every single grain of sand on our planet, there are dozens of stars in the observable universe. And even that staggering number only represents what we can see. The observable universe is limited by time. Light has only had about 13.8 billion years to travel to us since the Big Bang. Beyond that horizon, there could be more galaxies and more stars, possibly infinitely many. We just don't know. What we can say for sure is that 200 billion trillion stars exist within the region we can observe. At this point, the number stops being just a statistic. It becomes a context for our existence. Most stars have planets, which means the universe likely contains hundreds of billions of trillions of worlds. Even if life is incredibly rare, the sheer number of opportunities changes the conversation completely. Stars are separated by distances so enormous that even traveling near the speed of light, journeys would take centuries. Civilizations, if they exist, are likely isolated, separated, by oceans of silent space. Understanding this number reframes your place in reality. You are not at the center. Your sun is ordinary. Your galaxy is average. Your location is unremarkable. And yet, you exist. You are conscious matter in a universe that allows for consciousness. The atoms in your body were forged inside stars that lived and died billions of years before Earth even formed. You aren't separate from the cosmos. You are a direct continuation of it. This is why the number matters. Not because it's big, but because it changes your perspective. It reminds you that your problems are local and temporary, while the universe is vast and ancient. It humbles you without diminishing your worth. You don't need cosmic importance to have value. Being here, aware, and capable of understanding this scale at all is already extraordinary. Counting the stars is just the beginning. In our next video, we'll explore how they're born, how they live, how they die, and how this endless cycle shapes everything from galaxies to life itself. Thanks for watching. To truly grasp the number 200 billion trillion, we need to stop thinking about the stars as just numbers. A star isn't a tiny dot of light in the sky. It's a physical process, a long, unfolding story of gravity and energy. Once you understand what a single star really is, that huge number stops being an abstract concept and becomes something far more profound. Each one of those stars is an active engine, quietly and relentlessly shaping the universe. A star's life begins not in light, but in darkness. Long before it shines, it's just part of a vast, cold cloud of gas and dust drifting through space. These molecular clouds are enormous, sometimes stretching for hundreds of light years, and they're incredibly cold, just a few degrees above absolute zero. At these temperatures, atoms move so slowly that gravity can begin its quiet work. Most of the time, the cloud is stable, but then something disturbs it. A nearby supernova sends out a shockwave, or two clouds collide. Suddenly, gravity gets the upper hand, and a region begins to collapse. As all that gas falls inward, it heats up. Gravity converts potential energy into motion, and that motion creates heat. The collapsing cloud breaks into smaller clumps, and each one is destined to become a star. At the center of each clump, the pressure and temperature keep rising as more material falls in. Eventually, the core gets hot enough to ignite nuclear fusion. Hydrogen atoms start fusing into helium, releasing an enormous amount of energy. This is the moment a star is born. Fusion is what makes a star a star. It creates an outward push that perfectly balances gravity's inward pull, making the star stable. This stable, shining phase is called the main sequence, and how long it lasts depends almost entirely on the star's mass. Mass is destiny for a star. Small stars, like red dwarfs, live slow, efficient lives. They sip their fuel so slowly they can shine for trillions of years. The universe isn't even old enough for a single red dwarf to have died yet. Every red dwarf ever born is still out there, quietly glowing. Stars like our sun live a bit faster. A yellow dwarf like ours will spend about 10 billion years on the main sequence. Our sun is about halfway through its life, and for billions of years it has steadily turned hydrogen into helium, giving us the light and heat that made life on Earth possible. But one day, the hydrogen in its core will run out. The balance will break. The core will shrink and heat up, while the outer layers expand, turning our sun into a red giant, so large it might swallow the inner planets. Eventually, it will shed its outer layers, leaving behind a dense core called a white dwarfer, stellar ember, that will slowly cool over trillions of years. Massive stars live dramatically different lives. A star 10 times the mass of the Sun will burn through its fuel in just a few million years, not billions. These giant stars fuse heavier and heavier elements in their cores, hydrogen to helium, then carbon, oxygen, silicon, and finally, iron. Iron is the end of the road. Fusing iron doesn't release energy, it consumes it. Once the core fills with iron, fusion stops. Gravity wins in an instant. The collapse is catastrophic. In less than a second, the core implodes, crushing matter to unimaginable densities. It then rebounds violently, sending a shockwave racing outward. The star explodes as a supernova, briefly shining brighter than an entire galaxy. In that single, violent explosion, the star scatters all the heavy elements it forged out into space. Carbon, oxygen, iron, even gold and uranium, all of it is hurled across the cosmos. These elements seed the next generation of stars and planets. Every atom in your body, besides hydrogen, was created this way. The calcium in your bones, the iron in your blood, the oxygen you breathe. You aren't just metaphorically made of stardust. You are literally assembled from the remains of ancient suns. So, when we talk about 200 billion trillion stars, we're also talking about 200 billion trillion element factories that have been operating across cosmic time, slowly enriching the universe with the ingredients for complexity. And most stars don't live alone. The majority are born in pairs or groups, orbiting one another. These binary systems create some of the most extreme events in the universe. If one star in a close pair becomes a red giant, it can spill its material onto its companion, triggering violent outbursts or even a different type of supernova. When massive stars die, they leave behind the strangest objects imaginable. Neutron stars are cores so crushed that a teaspoon of their material would weigh billions of tons. They spin hundreds of times a second, flashing beams of radiation like cosmic lighthouses. And then there are black holes. If the collapsing core is massive enough, nothing can stop gravity. Space and time themselves warp inward, creating a region where nothing, not even light, can escape. So when we count the stars, we're not just counting shining suns. We're also counting quiet white dwarfs, spinning neutron stars, and invisible black holes. The universe's stellar population includes every stage of this incredible life cycle. Now think about that number again. 200 billion trillion isn't just a count of identical objects. It represents an unimaginably diverse population. Tiny red dwarfs, sun-like stars with planets, massive blue giants that live fast and die young, and the dense, dark remnants they leave behind. These stars aren't scattered randomly either. They gather into galaxies. Galaxies gather into clusters, and clusters arrange themselves into massive filaments and walls, separated by vast empty voids. On the largest scales, the universe looks like a cosmic web. Most of space is empty. Stars, for all their numbers, occupy a tiny fraction of the universe's volume. This emptiness is important. It means stellar collisions are almost non-existent, allowing planetary systems to remain stable for billions of years. It also means that life, if it arises, likely exists in isolated pockets, separated by immense distances. When you put it all together, the number of stars becomes more than a statistic. It becomes a framework for reality. A universe with this many stars is a universe where creation is abundant and complexity has had countless chances to emerge. But abundance doesn't guarantee life. It requires the right conditions, the right chemistry, and a lot of time. We know stars make planets common. Observations suggest most stars have at least one, meaning there are likely more planets than stars in the universe, hundreds of billions of trillions of worlds. A fraction of those orbit in the habitable zone where liquid water could exist. When we truly begin to understand that each of the 200 billion trillion stars is a separate sun, the next question naturally emerges: what surrounds these suns? Stars are rarely born alone. They almost always carry with them entire systems of planets, moons, dust, ice, gas, and slowly evolving worlds. This realization represents one of the most profound shifts in modern astronomy. Only a few decades ago, we knew with certainty of just one planetary system, our own. Today, we understand that planets are not rare exceptions, but the default outcome of star formation itself. Stars are born from vast, rotating disks of gas and dust. Whatever material doesn't fall directly into the forming star remains behind to create planets. This process is so natural and so common that most stars end up surrounded by worlds of every imaginable kind. Small rocky planets, massive gas giants, frozen ice worlds, superdense, super-Earths, and strange exotic objects that defy anything we see in our own solar system. When we look up at the night sky, we see only points of light. Yet around each of those points may exist entire planetary systems, quietly orbiting in the darkness, invisible to our eyes, but no less real. The sheer scale of this reality is overwhelming. If most of those 200 billion trillion stars possess planets, then planets themselves outnumber stars. This isn't philosophical speculation. It's observational fact. It's been confirmed by missions like the Kepler Space Telescope, which stared continuously at a single patch of sky, searching for the faintest dips in starlight caused when a planet passed in front of its star. From these tiny signals, we learned something astonishing. Planets are everywhere. Earth-sized rocky planets are common, not rare. And systems like our own are not unusual. Among all these worlds, there exists a special region around stars known as the habitable zone. This is where temperatures allow liquid water to exist on a planet's surface. Water is the foundation of all known life because it stabilizes temperature, enables chemistry, and allows complex molecules to interact in ways no other substance can. Now, habitable does not mean inhabited, but it does mean possible. Data suggests that between 20 and 50% of Sun-like stars may host at least one rocky planet in this zone. Even if we take the most conservative estimate and say only 20%, the resulting number is staggering. Trillions upon trillions of potentially habitable worlds scattered across the observable universe. Here, we encounter the power of large numbers. This brings us to the most unsettling question of all. If the universe offers so many chances for life, why does it appear so silent? Why haven't we detected unmistakable signs of other civilizations? This silence is not proof of absence, but rather a reflection of distance and time. Stars are separated by light years, civilizations by centuries or millennia of technological development. Communication across these scales is slow, fragile, and easily lost. A radio signal weakens as it travels, becomes noise, and may never be recognized as artificial by another intelligence. And even if two civilizations exist at the same time, the window in which both are capable of communication may be very brief. So the universe can be full of life and yet feel empty. As we consider planets and life, we are inevitably drawn back to our own existence. Earth is not an exceptional world orbiting an extraordinary star in a privileged position. It is a typical rocky planet orbiting a typical yellow dwarf star in the outer regions of a typical spiral galaxy. This ordinary nature is precisely what makes it profound, because it suggests that our existence arose not from cosmic rarity, but from universal rules. Stars form, planets form, chemistry unfolds, and under the right conditions, life emerges. And life eventually becomes curious, questioning its surroundings and counting the stars. This curiosity is itself extraordinary. Stars do not know they shine. Galaxies do not know they exist, but we do, and we are made from the very elements those stars created, forged in stellar cores, scattered by supernova, and assembled into living beings capable of reflection. This connection between the vast and the intimate is what makes the cosmic perspective both humbling and comforting. While we are small in scale, we are not insignificant in meaning. Scale does not determine value, experience does. The universe is vast enough to contain unimaginable numbers of stars, yet intimate enough to give rise to consciousness that can understand them. This understanding softens our fears. When we recognize our place within a universe so large, our personal anxieties shrink. Once we accept that the observable universe alone contains roughly 200 billion trillion stars, we're naturally drawn to a deeper, more unsettling realization. Everything we've discussed so far exists only within a boundary defined, not by physical walls, but by time itself. Because the observable universe isn't the entire universe. It's merely the portion of the cosmos from which light has had enough time to reach us since the beginning of cosmic expansion. This distinction matters profoundly. It means that beyond what we can see, there may exist vastly more stars, galaxies, and structures forever hidden from our view. Not because they're absent, but because the universe has not yet allowed their light to arrive. To understand this, we must return to the beginning, to the moment the universe itself began expanding, approximately 13.8 billion years ago. Space, time, energy, and matter emerged together in an event we call the Big Bang. Now, it's important to clarify. The Big Bang wasn't an explosion at a single point in space. It was an expansion of space itself, everywhere at once. Every region of space was once compressed into an incredibly hot, dense state. As space expanded, it cooled, allowing particles to form, atoms to assemble, and eventually, stars and galaxies to emerge. This creates a horizon around us, known as the cosmic light horizon, and this horizon defines the observable universe. But here's where intuition fails. Although the universe is 13.8 billion years old, the observable universe is not 13.8 billion light-years in radius. It's much larger, about 46 billion light-years in every direction. This apparent contradiction arises because while light was traveling toward us, space itself was expanding, stretching the distance between objects even as the photons moved through it. So, the galaxies that emitted the light we see today are now far, far farther away than they were when that light was released. This expansion means the observable universe has a diameter of about 93 billion light-years, an unimaginably vast sphere containing everything we can possibly observe. Within this sphere reside the 2 trillion galaxies and 200 billion trillion stars we've counted. But this sphere is not the edge of existence. It's simply the edge of visibility. Beyond it, space almost certainly continues, carrying galaxies and stars we will never observe. Their light will never reach us, either because it hasn't had time to arrive, or because cosmic expansion is accelerating, pulling those regions away faster than light can traverse the growing distance. This acceleration is driven by dark energy, a mysterious property of space itself that causes expansion to speed up over time. Because of dark energy, there are regions of the universe whose light will never reach us, no matter how long we wait, not even in trillions of years. These regions are permanently, causally disconnected from us. We can never observe them, influence them, or receive information from them. And yet, their existence is strongly implied by the uniformity of the universe we do see. Galaxies are distributed statistically evenly, and the cosmic microwave background radiation is nearly uniform across the entire sky. This suggests that the same physical laws and conditions apply far beyond our horizon. This leads to one of the most profound possibilities in cosmology, that the universe may be vastly larger than the observable universe. perhaps hundreds, thousands, or even infinitely larger. If the universe is infinite in extent, then the number of stars isn't merely enormous, but literally infinite. Not a large number, but an unending one, with galaxies repeating endlessly across space. In such a universe, every possible configuration of matter would occur somewhere, including galaxies identical to the Milky Way, planets identical to Earth, and even versions of ourselves living out similar lives. This concept sounds like science fiction, but it arises naturally from the mathematics of infinite space combined with the finite possible arrangements of matter. We must be careful here, though. Infinity isn't something we can observe, measure, or confirm. It's a theoretical implication. Current data can definitively tell us whether the universe is infinite or just extremely largely, that it's much larger than what we can see. So when we say 200 billion trillion stars, we're speaking only about the observable portion, the part of existence accessible to us by light. Beyond that number may lie vastly more stars, forever hidden beyond our cosmic horizon. This realization reframes our entire understanding of reality. It means that everything humanity has ever known, every star, every galaxy, every atom ever observes within a tiny bubble of a potentially far greater whole. This doesn't diminish what we see, it enhances it. It reveals that our measurements are not absolute totals, but local samples. And yet, even this local sample is unimaginably vast. This brings us to a subtle but important psychological shift. The universe isn't just big, it's open. It doesn't present itself as a closed system with clear boundaries, but as an expanding mystery where every answer reveals deeper unknowns. This openness can feel unsettling because humans naturally seek edges, conclusions, final numbers, but the universe doesn't offer them easily. Instead, it offers scales that dissolve intuition and horizons that recede as we approach them. In this context, the number of stars becomes not just a statistic, but a lesson in humility, patience, and perspective. Our minds evolved to handle immediate environments, small numbers, from the incomprehensible scale of the cosmic web, where galaxies stretch across billions of light years, we now journey inward. We're returning to the quieter, deeply rhythmic lives of individual stars. Why? Because every glowing filament, every cluster of galaxies, every spiral arm depends on one fundamental process: the birth, life, and death of a star. Stars aren't just static lights frozen in the sky. They are dynamic engines of change, evolving over millions, billions, and sometimes trillions of years. And the incredible thing is, a star's entire life path, how hot it burns, how bright it shines, how long it lives, and how it dies, is determined by a single property: its mass. This simple rule hides extraordinary complexity. Stars are born from vast, cold, molecular clouds. These are enormous regions of hydrogen, gas, and dust drifting through galaxies like slow-moving oceans, barely warmer than absolute zero. They remain dark and quiet until something disturbs them, maybe a shock wave from a nearby supernova, a collision between clouds, or the gentle gravitational squeeze from a galaxy's spiral arms. Once gravity takes hold, the process becomes inevitable. The gas collapses, fragments, and begins to spin. Dense cores form, heating up as they shrink, converting gravitational energy into thermal energy. At the heart of each collapsing fragment, a protostar begins to glow, not from fusion, but from the sheer heat of its own compression. It's surrounded by a swirling disk of leftover material, the very stuff from which planets will one day form. But at this stage, the star isn't truly alive. True stellar birth happens when the core becomes so hot and dense that nuclear fusion ignites. Hydrogen nuclei slam together with such force that they fuse into helium, releasing a tremendous amount of energy, as described by Einstein's famous equation, E equals mc squared. The moment fusion begins, the star enters the main sequence. This is the longest and most stable phase of its life, a perfect balancing act between the inward crush of gravity and the outward push of fusion. This quiet equilibrium can last for billions of years. During this time, stars shine steadily, converting mass into energy, illuminating their galaxies, warming planets, and slowly, patiently, shaping the chemical evolution of the universe. Most stars we see today are in this phase, including our own Sun. It's a middle-aged yellow dwarf, about halfway through its 10 billion-year lifespan. It fuses hydrogen at a calm, steady pace, not too fast, not too slow, just enough to sustain itself and the worlds that orbit it. But not all stars live such measured lives. Mass changes everything. Small stars, known as red dwarfs, are incredibly efficient. They burn their fuel so slowly, glowing dimly, that they can endure for trillions of years. That's so long that not a single one has reached the end of its life yet, because the universe itself isn't old enough. These faint stars are the silent majority, making up about 75% of all stars. Most of the 200 billion trillion stars out there are quiet red dwarfs, shining in the darkness, invisible to our naked eyes, but numerically overwhelming. At the other end of the spectrum, massive blue stars live fast and die young. They burn through their fuel at a furious rate, shining tens of thousands of times brighter than the sun. But their brilliant lives last only a few million years before they exhaust their cores. These stars are rare, but their influence is immense. They sculpt their surroundings with powerful radiation, stellar winds, and ultimately, spectacular supernova explosions. As any star ages, its internal balance shifts. When the hydrogen in the core runs low, fusion slows down, and gravity starts to win. The core contracts and heats up, while the star's outer layers expand dramatically. It transforms into a red giant, or four more massive stars, a red supergiant. This swelling phase marks the beginning of the end. The star is now burning different fuels in layers: hydrogen in outer shells, helium in the core, creating heavier elements and completely altering its structure. For a star like our Sun, the end is relatively gentle. Its outer layers will drift away to form a beautiful, glowing shell of gas called a planetary nebula. The core will be left behind, collapsing into a white dwarf, a dense, Earth-sized remnant that will slowly cool and fade over trillions of years. But for massive stars, the ending is far more violent. When they run out of fuel, their cores collapse catastrophically in less than a second. This triggers a supernova, an explosion so powerful it can briefly outshine its entire galaxy. In the intense heat and pressure of the blast, heavy elements like iron, gold, and uranium are forged. These elements, essential for life as we know it, are then scattered across space, seeding the next generation of stars and planets. We are, quite literally, made of stardust from these ancient explosions. These cosmic deaths are not rare. Across the observable universe, a supernova happens about once every second. Each one is a moment of creation, hidden within destruction. From these explosions, the most extreme objects in the universe are born: neutron stars and black holes. These are stellar remnants, so dense they warp the fabric of space-time itself. When we step back, we see that the universe has been performing this cycle for nearly 14 billion years. Stars are born, they shine, they die, and in doing so, they enrich the cosmos. The 200 billion trillion stars we can count today are just the current survivors of this long history. Countless others lived and died before them, meaning the total number of stars that have ever existed is far greater than what we see now. This adds a profound temporal dimension to our cosmic senses. The universe is not only vast in space, but incredibly deep in time. Stars are the threads connecting these dimensions, carrying matter forward through generations, transforming simple hydrogen into the complex chemistry required for planets and, eventually, life. Within galaxies, these stellar life cycles drive evolution. Star formation heats up gas, supernova inject energy, and stellar winds push material around. These are slow, patient processes, measured not in human lifetimes, but in billions of years. It gives the universe a calm, unhurried character. There's something deeply comforting about this rhythm. Nothing in the cosmos rushes. Stars don't hurry to be born or fear their death. Galaxies don't panic as they merge. The universe unfolds at its own pace, completely indifferent to our clocks and calendars. When we tune into this cosmic rhythm, our own anxieties can soften. We are temporary expressions within a system that is vast, ancient, and ongoing. Our existence may be brief, but that doesn't make it meaningless. Meaning doesn't require permanence. It requires awareness, and we are aware. We are aware of the stars, of the galaxies, of our place within this immense and beautiful process. That awareness is an astonishingly rare phenomenon in a universe that is otherwise silent. But stars don't exist in isolation. They form families, clusters, binaries, and complex systems where gravity binds them together. These interactions can dramatically alter their destinies. To truly understand stars, we have to understand their social lives, and that's where we're headed next, as we explore star clusters, binary systems, and the intricate ways stars live together within their galactic neighborhoods. Thanks for watching. If you enjoyed this journey through the lives of stars, be sure to subscribe for more explorations of our incredible universe. When we look up at the night sky, we often think of stars as lonely points of light, separated by vast, empty distances. This story begins at birth. Stars emerge from the same collapsing molecular cloud, which fragments into dozens, hundreds, or even millions of sibling stars. Though the scales are unimaginably different, the patterns resonate. As we journey from the social lives of stars to their final, most extreme fates, we enter a realm where our everyday intuition starts to dissolve. Neutron stars and black holes aren't just objects floating in space. They're expressions of physics pushed to its absolute limits. They are formed when massive stars run out of fuel and gravity wins its final crushing victory over every force that once held the star stable. These cosmic remnants are rare compared to ordinary stars, but their influence is immense. They shape entire galaxies, produce the most energetic events in the universe, and reveal how matter and spacetime behave under conditions we could never hope to create on Earth. This journey to the extreme begins with the death of massive stars, many times heavier than our own sun. These giants live fast and die young, burning through their nuclear fuel at a furious pace. When a star like this finally creates an iron core, its life is over. Iron can't release energy through fusion, so the delicate balance between outward pressure and inward gravity is broken. In a fraction of a second, the core implodes. Matter is compressed to unimaginable densities. In this inferno, electrons and protons are forced together to become neutrons. A single teaspoon of its material would weigh billions of tons. This incredible density creates gravity so intense that space-time itself curves sharply around it. When these magnetic poles don't line up with the star's rotation axis, they sweep beams of radiation through space like cosmic lighthouses. If Earth happens to be in the path of one of these beams, we detect regular pulses of energy. Pulsars have taught us so much about Einstein's relativity, nuclear physics, and how matter behaves at densities far beyond anything we know. But even a neutron star isn't the ultimate end. Not the pressure of neutrons, not the strongest nuclear forces, nothing. The core continues to shrink until it becomes a black hole, a region of spacetime where gravity is so powerful that nothing, not even light, can escape. Black holes aren't defined by a solid surface, but by an event horizon. Once something crosses it, any information about it is lost to the outside universe forever. Now, while black holes sound terrifyingly destructive, they're surprisingly passive most of the time, just quietly existing in space. They only become active when matter strays too close. Friction and gravity heat this disk to millions of degrees, causing it to glow intensely with X-rays and other high-energy radiation. In some cases, this process powers colossal jets of particles, blasting out from the black hole at nearly the speed of light. These jets can stretch for thousands, or even millions, of light years, influencing star formation and the evolution of entire galaxies on a grand scale. And it gets even more astonishing. While stellar mass black holes form from dying stars, there's a whole other class found at the centers of galaxies: supermassive black holes. These behemoths contain millions or even billions of times the mass of our Sun. It seems nearly every large galaxy has one, including our own Milky Way. Our galaxy's central black hole, Sagittarius A*, weighs about 4 million suns and quietly governs the orbits of stars at the galactic core. These supermassive black holes likely formed early in cosmic history, growing rapidly by merging with other black holes and accreting huge amounts of gas and dust. During their most intense feeding frenzies, they power quasars, the brightest objects in the entire universe, visible across billions of light years. Quasars aren't just spectacular cosmic lighthouses. They are agents of change. The energy they blast out can heat up and blow away gas from their host galaxies, regulating the birth of new stars and shaping how galaxies grow. This reveals a profound cosmic cycle. The death of stars creates black holes, and those black holes, in turn, influence the birth of future stars. It's a cycle that operates on scales from a few kilometers to millions of light years. When we try to count all the neutron stars and black holes in the observable universe, the numbers are staggering. Estimates suggest hundreds of millions of neutron stars and billions of black holes are scattered throughout the galaxies, silent and unseen unless they're interacting with something nearby. These objects remind us that so much of the universe is invisible. It's not empty, it just doesn't emit light we can see. This invisibility extends even further. There's dark matter, which outweighs all the normal matter we see by a factor of 5 to 1, forming the invisible skeleton of the cosmos. And then there's dark energy, the mysterious force driving the accelerating expansion of the universe, ensuring that even as gravity binds things together locally, the universe as a whole continues to stretch, cool, and expand. In this grand context, neutron stars and black holes aren't anomalies. And while these extremes might seem frightening at first, when we look at them from a cosmic perspective, they're just part of the universe's ongoing story. After exploring the violent beauty of neutron stars and black holes, the universe now invites us into a much quieter chapter, one that unfolds not in explosions or intense radiation, but in slow, fading, cooling, and deep time. While stars are born and die, the universe as a whole is moving steadily toward a future defined less by activity and more by stillness. This future isn't sudden or catastrophic, but gradual, stretched across trillions upon trillions of years, far beyond any human scale of experience. To understand this future, we must first recognize that star formation is not eternal. It depends on cold gas, and gas is a finite resource. Although the universe once formed stars at a furious pace during its early youth, that era has long passed. As galaxies age, their reservoirs of gas are slowly consumed by star formation, blown away by stellar winds and supernova, or heated to temperatures too high to collapse again. Today, the universe forms stars at only a fraction of the rate it once did, a slow decline that will continue inexorably. In galaxies like the Milky Way, only a few new stars are born each year, while billions quietly age and evolve. Eventually, perhaps in 1 trillion years or so, most galaxies will have exhausted their usable gas entirely, bringing star formation to an end. When the last stars are born, the universe will enter a new era, often called the Stelliferous Era's twilight, a time when no new lights ignite, and the existing stars slowly fade one by one. The nature of this fading depends strongly on stellar mass. The massive blue stars will disappear first, having already lived and died long ago, while sun-like stars will persist for billions more years before swelling into red giants and becoming white dwarfs. Red dwarfs, the most numerous stars in existence, will dominate this future sky, glowing dimly but enduring for trillions of years. Their nuclear reactions are so efficient that they sip their fuel rather than burn it. During this unimaginably long epoch, galaxies will still exist, still orbit, still drift, but their appearance will change, becoming redder, dimmer, and quieter as bright young stars vanish, leaving behind faint, ancient populations. Over time, even the red dwarfs will exhaust their fuel, cooling into black dwarfs, hypothetical objects that have not yet had time to exist because the universe is still too young. As this happens, the universe will grow darker, not suddenly, but gradually, as lights wink out across cosmic time. Alongside this stellar aging, cosmic expansion continues, driven by dark energy, pulling galaxies farther apart, accelerating their separation until distant galaxies slip beyond the cosmic horizon, their light stretched so thin it can no longer reach us. In the far future, observers within any given galaxy will see fewer and fewer external galaxies, until eventually only their own local group remains visible, isolated in an otherwise empty sky. This isolation marks a profound shift in cosmic perspective. Future astronomers, if any exist, may conclude that their galaxy is the entire universe, unaware of the countless others that once filled the sky but have since vanished beyond reach. This future loneliness of galaxies mirrors the eventual loneliness of stars themselves. As star formation ends and stellar remnants dominate, the universe becomes populated mainly by white dwarfs, neutron stars, black holes, and cold planetary bodies drifting through space. Yet, even in this darkness, change does not completely stop. Gravity continues to act, slowly pulling objects together. black holes merge, stellar remnants interact, and rare events still occur over immense spans of time. One of the most fascinating aspects of this distant future involves black holes. Although they are often thought of as eternal, they are not. According to our current understanding of physics, black holes slowly lose mass through a process known as Hawking radiation, an incredibly weak emission of particles arising from quantum effects near the event horizon. For stellar mass black holes, this process takes far longer than the current age of the universe, perhaps 10 to the power of 67 years or more. For supermassive black holes, it may take 10 to the power of 100 years or longer, numbers so large they defy intuitive meaning. Yet even these giants will eventually evaporate, leaving behind a universe with no stars, no black holes, only a thin soup of particles drifting through ever-expanding space. This scenario is often referred to as the heat death of the universe, where energy is evenly distributed, no gradients remain, and no work can be done. While this description may sound bleak, it is not violent or frightening. It is simply quiet, a natural outcome of thermodynamic laws applied over infinite time. Importantly, this future is so distant that it has no bearing on any life, civilization, or concern we can imagine today. Instead of invoking despair, it invites a sense of peace. It shows that the universe is not rushing toward an end, but easing gently into rest. When we place ourselves within this timeline, our brief lives become less pressured, because nothing is demanded of us by cosmic necessity. The universe does not require urgency, productivity, or legacy. It simply unfolds. This understanding allows us to release anxiety about permanence, because permanence is not the goal of existence, experience is. Right now, in this moment, the universe is bright, filled with stars, galaxies, and possibilities, and we are here to witness it during one of its most vibrant chapters, a time when stars still shine, planets still orbit, and life can still emerge. This perspective transforms cosmic impermanence from a source of fear into a reminder of value, because rarity does not diminish meaning, it enhances it. The fact that conscious beings exist during a brief, luminous era of the universe is remarkable. As we rest with this thought, the future no longer feels threatening but expansive. A vast timeline within which our moment exists naturally, neither too early nor too late. Having now traced the life cycles of stars and the long arc of cosmic time ahead, the next step is to return once more to the present, to consider what all of this means for us now, how understanding the universe's past and future reshapes our view of existence, purpose, and perspective. In the next part, we will explore the human place in the cosmos, not as conquerors or outsiders, but as participants within an immense and ongoing story. After our journey through the immense future of stars and galaxies, the mind naturally turns inward. What does all of this mean for us, for human beings living brief lives on a small planet, orbiting an ordinary star? Understanding the universe at this scale doesn't erase humanity. It reframes it. It places us not at the center of existence, but deeply within it. This shift in perspective is one of the most powerful gifts of cosmic understanding. For most of human history, our view of reality was small and local, defined by the horizon, the sky, and stories passed down through generations. Yet, in just a few centuries, we expanded that view outward. We built tools that extended our senses far beyond biology. allowing us to see distant galaxies, measure ancient light, and reconstruct the history of the universe itself. This achievement is extraordinary, not because of domination or conquest, but because it represents curiosity made real matter that learned to question itself. When we say that humans are insignificant on a cosmic scale, we often misunderstand what significance truly means. Size alone does not determine importance. Awareness does. The universe contains countless stars, but stars don't wonder why they exist. Galaxies don't contemplate their future. Black holes don't ask questions about meaning. And yet, here we are, beings made from star-forged atoms, capable of reflection, capable of understanding where we came from and where we are going. This capacity doesn't elevate us above the universe, it binds us more deeply to it. We are not separate observers looking in from the outside. We are participants, expressions of the same physical laws, operating at a different level of complexity. When we grasp this, the universe no longer feels cold or indifferent. It feels vast and neutral, a place where meaning is not assigned from above, but created through experience. This realization can be profoundly calming. It removes the pressure to matter on a cosmic scale, freeing us to matter on a human one. We can care about moments, relationships, curiosity, and quiet understanding. Knowing that the universe doesn't demand a grand purpose from us, it simply allows us to exist within it. When we consider our planet in this context, Earth becomes both ordinary and precious. Ordinary because rocky planets orbit stars everywhere. Precious because this one is home to life that can think, feel, and understand. Our position in the Milky Way is similarly unremarkable, yet fortunate. We're located far from the chaotic core, in a stable spiral arm, in a region with relatively few nearby supernovae over geological time. These were the conditions that allowed complex life to evolve without constant cosmic disruption. This balance between chance and law is central to understanding humanity's place. Our existence is not guaranteed by the universe, but it is permitted by it. And within that permission lies responsibility, not to the cosmos, which will continue regardless, but to ourselves and to the fragile systems that support life here. When we look outward and see billions of trillions of stars, it becomes clear that the universe does not revolve around us. Yet, it also becomes clear that our perspective is rare, and rarity gives value. Consciousness may be uncommon, even in a universe filled with planets. Intelligence capable of understanding cosmic history may be rarer still. This possibility adds weight to our brief moment, not in terms of dominance, but stewardship. If awareness is uncommon, then preserving it matters. This doesn't mean believing we are unique or chosen. It means recognizing that experience itself is something worth protecting, wherever it arises. When we contemplate the future of humanity against the backdrop of cosmic time, the contrast is stark. Civilizations last thousands of years, while stars last billions, and galaxies last trillions. Yet this doesn't diminish civilization, it contextualizes it. It shows that endurance is not the measure of worth, and that even fleeting phenomena can be meaningful within their own scale. The challenge humanity faces is not to conquer the universe, but to survive long enough to continue asking questions, to continue learning, to continue experiencing wonder. Whether we remain confined to Earth or eventually spread to nearby stars, the fundamental task remains the same: to navigate our technological power with wisdom. The universe does not threaten us directly. Most threats we face are of our own making. The cosmic perspective can help soften destructive impulses by reminding us how small and interconnected we are, and how fragile the conditions for life can be. When we step back and see Earth as one world among countless others, it becomes easier to care for it, not because it is central, but because it is home. And home does not need to be unique to be worth protecting. As we rest with these thoughts, the universe becomes less overwhelming and more intimate. Its vastness doesn't diminish our experiences. It frames them, allowing joy, curiosity, and calm to exist without cosmic pressure. The stars above no longer feel distant or judging, but simply present, silent companions in a shared existence. As we move toward the final chapters of this series, the next step is to return once more to the numbers that began this journey, not to overwhelm, but to integrate, to understand how counting stars ultimately leads back to understanding ourselves. In the next part, we will revisit the question of scale, not as an abstraction, but as a perspective, exploring how the vastness of the universe reshapes the way we think, feel, and live within our brief moment. Thanks for watching, and I hope you'll join me for the next part of our journey. When we think about the universe, we often get caught up in the numbers. 200 billion trillion stars, trillions of galaxies, billions of years. But let's set the numbers aside for a moment and think about scale, not as a number, but as a way of seeing. When we do that, the universe starts to feel less like some overwhelming, crushing expanse, and more like a quiet teacher, patiently showing us a new way to understand our own existence. You see, cosmic scale isn't asking us to compare ourselves to the stars just to feel small. It's inviting us to see ourselves clearly, to find our place within a much larger context. And that distinction is everything. Feeling small can be either diminishing or liberating, and it all depends on how you look at it. When we truly grasp scale, not just in our heads, but in our hearts, something subtle shifts inside us. Scale has this incredible ability to reframe what's important. It shows us that not everything has to be immediate or dramatic or permanent to be meaningful. The universe demonstrates this lesson all the time. Stars take millions of years to form. Galaxies take billions to evolve. The vast cosmic structures we see will take trillions of years to fade away. And within this immense, slow rhythm, our lives are a brief but vivid moment. We're like a single spark in a long, quiet night. We're not insignificant, just brief. And this brevity doesn't erase our meaning, it concentrates it. Our moments become so valuable precisely because they're limited. When we look at ourselves against the backdrop of cosmic time, that pressure to leave some eternal, monumental mark just dissolves. It's replaced by a much quieter invitation to experience, to understand, to care, and to simply be a witness to it all. This is why thinking about the cosmos can be so deeply calming. It removes the illusion that everything depends on us, on our actions, on our successes. It frees us to simply exist, to be part of the grand, unfolding story of the universe. So, as we come back to those mind-boggling numbers, we start to realize they were never meant to be memorized for a quiz. They were meant to change how we feel. Numbers at this magnitude aren't practical, they're philosophical. They stretch the mind until it finally lets go of its need to control everything. and in that release, we find peace. The universe isn't something to be conquered or mastered. It's something to be understood gently, layer by layer. When we stop trying to dominate the idea of scale and instead just let it wash over us, the universe becomes less intimidating and more serene. It's like standing at the edge of the ocean at night. You can feel its immense depth without needing to measure it with a ruler. This feeling naturally extends into how we relate to ourselves and to others. When we truly recognize how vast existence is, our personal conflicts and disagreements lose some of their sharp edges. It's not because they suddenly become unimportant, but because we see them for what they are, temporary. This perspective encourages compassion, patience, and a deep sense of humility. And humility, in this context, doesn't mean putting yourself down. It means accurate self-placement. It's about knowing where you stand without exaggeration or erasure. And this accurate placement reveals something truly beautiful. That we are both completely ordinary and utterly extraordinary at the same time. We're ordinary because we're made of the most common elements in the cosmos, star stuff found everywhere. But we're extraordinary because those same common elements have somehow arranged themselves into consciousness, into an awareness that is capable of looking back out and understanding the very universe that produced it. This duality is at the heart of cosmic meaning. It shows us that significance isn't about being unique or being the biggest. It's about experience. The universe may be vast and mostly empty, but within that emptiness, these little pockets of complexity arise, where matter becomes curious. And that curiosity isn't some cosmic accident. It's a natural outcome of complexity interacting with time. So when we gaze up at the stars, we're not just looking at something separate from us. We're contemplating our own origins and our own future. Every single atom in our bodies was once forged inside a star. And one day, billions of years from now, those same atoms will return to the cosmos, recycled into new generations of stars, planets, and perhaps new life. This continuity dissolves the boundary between self and universe. It reveals existence as a constant flow, not a static state. It's a flow that is slow, gentle, and constant, operating on a timescale far beyond our human comprehension. Mentally aligning with this flow can be deeply restful. It's a powerful reminder that not everything needs to be resolved right this second, not on a cosmic scale. As we learn to rest within this understanding, the universe becomes a place of belonging, not alienation. We aren't just visitors here. We are a product of this place. The same fundamental laws that shape the galaxies also shape us: gravity, energy, time, and entropy. Recognizing this shared foundation builds a quiet intimacy with existence itself. The stars feel less distant and more familiar, not as objects we can touch, but as processes we are part of. This sense of familiarity softens our fear. Fear so often arises from a feeling of separation, from feeling out of place in the world. But a cosmic perspective restores our sense of placement. It shows us that we are exactly where we are supposed to be, at this exact moment, in this particular era, luminous chapter in the universe's long story. And while this chapter will one day end, that ending doesn't negate its beauty. A stunning sunset doesn't diminish the day that came before it. This metaphor extends to our lives. Our lives end, but the experiences we have are real while they are happening. The universe doesn't demand permanence to grant validity. It allows transient, fleeting moments to be whole and complete in themselves. This idea is deeply compatible with rest, with sleep, with the act of letting go. It removes that frantic need to hold on to everything, to make everything last forever. Instead, it encourages a quiet trust in the unfolding process. When we allow ourselves to rest within this trust, the universe becomes a quiet companion rather than an overwhelming presence. Now we can start to understand why so many cultures, for so many thousands of years, have found comfort in looking up at the night sky. It offers us perspective without judgment. It gives us a sense of scale without pressure, and it shares its beauty without making a single demand. As we approach the end of this journey, those numbers that once seemed so abstract and intimidating now feel different. They feel integrated, woven into a larger, more peaceful understanding of existence, where scale informs meaning instead of erasing it. This prepares us for our final reflection, where we bring all these ideas together, the stars, time, scale, life, and awareness into a single calm thought. We're not here to answer every question, but to simply rest with what we have learned. In our next and final part, we will gently conclude this exploration, weaving all these threads into a final perspective on what it means to exist in a universe so vast, so old, and so quietly magnificent. Thanks for watching, and I'll see you in the finale. As everything we have explored begins to settle into a single, quiet understanding, the universe no longer feels like a collection of separate facts. It feels like a continuous story where scale, time, matter, and awareness are woven together into one slow, unfolding process. This synthesis isn't something that demands effort to grasp. It emerges naturally when we allow ourselves to stop resisting vastness and instead rest within it. Throughout this journey, we have moved outward from the human mind to stars, from stars to galaxies, from galaxies to the cosmic web, and then inward again toward meaning. And in doing so, we've discovered that the universe doesn't diminish us by being large, it contextualizes us. Context isn't erasure, it's grounding. And when we are grounded, fear loses its intensity, urgency loses its edge, and existence feels less like a challenge to be solved and more like a reality to be experienced. This is perhaps the most profound lesson the universe offers, that being here is enough. The cosmos doesn't demand justification for existence. It simply allows it. And within that allowance, complexity, beauty, curiosity, and consciousness arise. None of these require cosmic permission or permanence to be valid. They simply occur where conditions allow. And that allowance has existed for nearly 14 billion years, producing stars that shine, galaxies that rotate, planets that form, and life that wonders. When we see ourselves as part of this chain rather than separate from it, the universe feels less distant and more intimate, because intimacy doesn't require proximity, it requires origin. We share an origin with everything we see, and even with what we cannot see. This shared origin dissolves the sense of isolation that often accompanies thoughts of cosmic vastness. Isolation comes from feeling out of place, and we are not out of place. We are exactly where the laws of physics, chemistry, and time naturally led. Understanding this creates a quiet confidence, not arrogance, but belonging. Belonging doesn't mean being central. It means being included. And the universe includes us effortlessly, without ceremony or exception. When we accept this inclusion, we stop asking whether we matter in some ultimate sense and start appreciating that matter itself has arranged into something capable of asking questions. This shift changes how we interpret meaning. Meaning no longer needs to be imposed from outside. It arises from experience itself, from perception, from connection, from awareness. And awareness is real, even if temporary. Temporary does not mean trivial. Everything meaningful is temporary. Stars burn out, galaxies fade, civilizations end. Yet during their existence, they are complete. Completeness doesn't require eternity. It requires presence. The universe seems to understand this deeply. It doesn't rush toward outcomes. It unfolds slowly, patiently, allowing each phase to exist fully before transitioning into the next. This patience is reflected in cosmic time, where millions of years pass unnoticed, where processes operate without urgency. Aligning ourselves mentally with this pace can be deeply restorative. It allows us to release the pressure of immediacy, the idea that everything must be decided, achieved, or resolved now. Instead, we learn to trust that existence is a process rather than a destination. When we look at the stars with this understanding, they no longer feel like unreachable objects. They feel like fellow participants in a shared unfolding, born, shining, changing, and eventually fading, just as everything does. This shared impermanence isn't a flaw. It's the mechanism through which novelty and complexity arise. Without endings, there could be no beginnings. Without death, there could be no recycling of matter. Without change, there could be no evolution. This is why thinking about the universe before sleep can be so comforting. It replaces personal concerns with a larger rhythm, not to minimize those concerns, but to give them space to breathe. And in that space, tension softens, thoughts slow, and the mind becomes receptive rather than reactive. The stars above become companions in this slowing, distant yet constant, unchanged by our worries, shining whether or not we observe them. This constancy can be reassuring because it suggests that existence continues regardless of individual struggle, not in a dismissive way, but in a stabilizing one. It reminds us that we are held within something far larger than ourselves. Being held does not require awareness on the part of the holder. Gravity holds planets without intention. The universe holds stars without care or concern. Yet the holding is real, and we exist within it. This existence doesn't require explanation beyond the laws that allow it. When we accept this, questions of ultimate purpose lose their sharpness, replaced by a quieter appreciation for being here at all. This appreciation doesn't negate curiosity, it deepens it. As we arrive near the quiet end of this long journey, the universe no longer feels like something to analyze or measure, but something to rest within. After moving through stars, galaxies, time, and scale, the most natural response isn't excitement or urgency, but stillness. It's a gentle acceptance that understanding doesn't always require motion, and that perspective itself can be a place of rest. In this stillness, the cosmos reveals one of its most subtle lessons, that vastness doesn't demand effort, it allows being. And this allowance is what makes the universe feel safe rather than overwhelming when we approach it with patience. Nothing in the cosmos asks us to keep up with it. Stars don't rush. Galaxies don't hurry to collide. Time itself unfolds without anxiety. Aligning our thoughts with this pace can feel like exhaling after holding your breath for far too long. When we consider how long the universe has existed, nearly 14 billion years, and how much longer it will continue, stretching trillions of years into the future, our own moment becomes a calm pause within an immense flow. It's not a test or a race, but a temporary still point where awareness briefly gathers. And this awareness doesn't need to accomplish anything cosmic to be valid. Simply perceiving is enough. When we lie beneath the night sky, or even just imagine it while drifting toward sleep, we are participating in a relationship older than memory. Humans have always looked upward, not to dominate the stars, but to feel oriented, grounded within something larger. And while our ancestors didn't know the distances or the numbers, they sensed the same quiet order, the same slow movement, the same stability that exists right now. This continuity across generations suggests that cosmic comfort doesn't depend on knowledge, but knowledge can deepen it. Understanding removes fear without removing mystery, and mystery remains gentle when it's not threatening, when it's allowed to exist without any demand from us. The universe is full of such gentle mystery, dark matter we can't see, regions beyond our observable horizon we can't reach, futures we can't witness, yet none of this creates urgency. It simply exists. Learning to coexist with the unknown is one of the most restful skills the cosmos teaches, because uncertainty doesn't always require a resolution. Sometimes it requires trust. And trust, in this context, isn't belief in certain outcomes. It's trust in the process, in the idea that existence unfolds according to patterns that don't need our control. When we release the need to control, tension fades. So much of our anxiety arises from believing that everything must be managed, solved, or secured. But the universe quietly demonstrates that nothing on its scale is managed that way, and yet it works. Structures form, stars shine, life emerges. This process doesn't require intention or supervision. It arises naturally from interaction and time. Recognizing this allows us to soften our grip on our own lives. It helps us understand that not everything must be decided right now. Not every path must be clear. Clarity often arrives slowly, the way stars form from cold clouds, the way galaxies assemble over billions of years. When we align with this slow unfolding, we become more patient with ourselves, less harsh, more forgiving. This internal shift mirrors the cosmic balance we've observed throughout this journey. Balance between gravity and expansion, between birth and death, between order and freedom. These balances exist everywhere, not because they were designed, but because extremes resolve themselves over time. And this resolution is gentle, not forced. When we reflect on the 200 billion trillion stars we imagined earlier, they no longer feel like an overwhelming statistic. They feel like a quiet background presence, a reminder that light exists everywhere, even if it's far away, even if it's unseen. And this is comforting because it suggests that darkness isn't absence. It's simply the space between lights, and space itself isn't empty in a negative sense. It is potential, the medium through which everything moves and exists. This perspective reshapes how we experience our quiet moments. Silence is no longer emptiness. It's the space that allows thought to slow, breath to deepen, and awareness to rest. The universe is full of silence, vast regions where nothing happens for millions of years. Yet these regions are not meaningless. They are part of the structure that allows meaning to arise elsewhere. In this way, the cosmos validates rest, not as inactivity, but as a necessary balance. And this validation can be deeply reassuring when the mind is tired, when thoughts loop, when days feel heavy. It suggests that slowing down is not failure. It is alignment. Alignment with the universe's pace brings a sense of belonging that doesn't require achievement. As we allow this feeling of belonging to settle, the idea of being small transforms from something diminishing into something comforting. This is where the journey naturally comes to rest. Not because there is nothing left to say about the universe, but because everything that truly matters has already settled into place. Allowing the immensity we have explored to soften into something familiar rather than distant. Because by this point, the cosmos no longer feels like an abstract concept made of numbers and distances. And this shift is important, because understanding is not only about collecting information, it is about changing how we feel inside our own existence. Not dramatic gratitude, but quiet appreciation for the simple fact of being here at all. Knowing this allows us to rest more easily with impermanence, because it no longer feels like erasure. It feels like integration into something larger. Just as stars fade at dawn, not because they stop existing, but because our perspective changes. Sleep is like that. Consciousness dims, but existence continues. The universe does not pause because we rest. It carries us along, holding us the way gravity holds stars in orbit. Not tightly, not aggressively, but reliably. Trusting this holding allows the body to relax. Muscles soften, breath slows, thoughts drift apart. And when the mind begins to wander, it does so without fear, because it understands now that wandering is safe. The universe itself is wandering outward, expanding endlessly, and nothing breaks because of it. So as this final part closes, there is nothing left to instruct or reveal. Only the invitation to remain in this calm awareness for as long as it feels natural. And then to let it dissolve into sleep, knowing that when consciousness returns, the universe will still be there. Stars will still shine, galaxies will still turn, and our place within it will remain exactly what it has always been: small, temporary, connected, and enough. And with that understanding, we can rest completely, because the cosmos does not require us to stay awake. It only requires that we exist for the brief moment we are given. And tonight, that moment is allowed to end gently.